Hello everyone, good morning. I'm Kaushik, I'm with Argonne. So today I'll be talking about why we are using DAOS for our AI workloads and how we are using DAOS for our AI workloads. And to start with, Aurora is one of the largest and the fastest supercomputers in the world. We have around 10,000 compute nodes and more than 100,000 GPUs. And DAOS is the major file system on Aurora with 1024 DAOS nodes with a total capacity of 230 petabytes and a bandwidth more than 25 terabytes per second. We still rank number one in IO 500. So distributed deep learning AI frameworks, there are a lot of frameworks out there, and some of them have left, some of them stayed back. So this is a quick Google Trends that I pulled today over the last 5 years, trends on the search. So we clearly see that TensorFlow is going away, and there are very few people who are using TensorFlow, and it's at least at Argonne, at ALCF, we support these three frameworks, which is PyTorch, JAX, and TensorFlow. And I would say 90% of our AI workloads use PyTorch today. So PyTorch provides a rich ecosystem for AI workloads, high-level APIs, and execution models to run on different GPUs, and rich collective communication libraries. Also, we are the ACM Garden Bell finalist on running this AI workload on 10,000 compute nodes, where we achieved a sustained 10 exaflop in mixed precision. So another key important application at Argonne is Aurora GPT. Unlike general GPTs, we focus on training from scratch on for foundational science models. So we curate rich structured data sets from different science domains. We train on them on Aurora, and we fine tune for different particular science domains. So this is one of the largest workload on Aurora for AI. So as we have seen, increasing the number of parameters gives new emerging properties, and over the years, the size of the model has been continuously growing. So this leads to growing from billion parameters to trillion parameters, and the data set is obviously growing. So on Aurora, we have on one single compute node, we have a terabyte of CPU memory and less than a terabyte of GPU memory. Where DAOS comes into play is we have to load a lot of data sets, models, and checkpoint, and we have to avoid a lot of starvation and idle time. So this can bring the training time from several weeks to months. So the different distribution methods which PyTorch offers, I'm showing just the two here, which is model parallelism. So suppose we have 6 GPUs, and if the model is so big which we can fit in a GPU, we split the models into different GPUs. And this one is data parallelism, where each GPU can fit the entire model, but the data set is so big, we have to shard them on different GPUs. So in the data parallel training, each GPU has a complete copy of the model. The global batch is split into multiple mini batches, and the IO workers are prefetched and loaded in parallel, and they update the gradients and losses and keep repeating. So the key here is to continuously feed the model without any idle time. So as we have seen, the model size and the data set has been continuously growing. So the model parallelism and data parallelism is not sufficient enough to keep up with the demand, and PyTorch offers other strange, crazy parallelism methods like pipeline parallelism, tensor, expert sequence, and context parallelism. And most often we use a combination of a few of these, like a combined model parallelism and data parallelism. So how can DAOS help with IO pipeline for AI? So we need to load the data set faster, we need to load the model faster, and with checkpointing at scale. And DAOS offers a rich software ecosystem with POSIX interface, S3, MPIO, Hadoop, PyTorch. And we also have lower level access with a DFS interface. So on Aurora, for our AI workloads, we primarily use these two interfaces. One is with POSIX, where you would feel just pointing to a path, but we have to mount the POSIX container on all the 10,000 nodes. We can also use the lower level DFS interface, which would be closer to the hardware performance, and there are some interception libraries which would enable POSIX to give close to DFS performance as well. So PyTorch DAOS data loader provides an easy and convenient way to deal with data loaders as well as checkpointing. So on the top, I'm showing the way we load data from the POSIX container. So here I'm mounting the DAOS on /temp, my pool name and container name. So with the PyDAOS interface, all I have to do is just provide the pool name and the container name, and this would give us the DFS interface. So with PyDAOS, the reads and writes are DFS writes and DFS reads, which are faster than POSIX, and PyDAOS use DFS containers. And another advantage is the mounting time, so we don't have to mount the entire container on DFS. Also with checkpointing, it's pretty straightforward. You just point the pool and the container name. So the key here is the convenience and avoiding the mounting time, and it's very less code changes if I have to port any AI workloads to start using PyDAOS. So this is a quick result from running on a single compute node. There is roughly, I would say, 20% performance gain with PyDAOS, but at 10,000 node scale, it would be like saving few days for us, and it avoids mounting time. The future work is to do some performance and scaling studies, and we would be using PyDAOS for most of our AI workloads. That's it.
Do you have questions